Hello everyone and welcome back to WebAssembly. Today we are going to be looking at, continuing on what we looked at last time with the structures and encoding and decoding them. This video we're going to be addressing some of the issues that were in the previous one and then adding a couple of features so that we can actually use this framework and this library across multiple, or for how many ever purposes we want. So we'll start by looking at structure alignment. So let me turn the music down a little bit. And going to find WebAssembly. And we're going to go to desktop. And here we are. Okay. So what we have right now is we have this we have this little structure here that we looked at, and it wasn't working. So when we looked at our numstruct.html file, we created this structure that had a couple integers, and then there was another HTML file here, basic framework, that had a couple integers, and then there was a long and a char. Now, what was the problem was that it wasn't actually able to identify, or it wasn't able to encode these values properly. And what we found out, or I guess what I found out in an investigation, was the structure alignment wasn't accounted for. So when we made our initial, the way we write to memory in our framework is we just take the sizes of these respective variables, allocate and write that specific number of bytes. However, that's not specifically how memory in C is managed. With structures like this, there's going to be an overhead or an alignment that will determine how we actually store values. So let's look at the structure. There's an integer and an integer, or let's look at the substructure first. So this one is going to be substructure. So if we just have an element substructure, one of these values or one of these pieces of memory will look like this. So we'll have 5, 6, 7, and 8. So we'll have 8 bytes for the long. So this will be long. However, we still have another char, and you might think, well, okay, just tack that on at the end. But that's not exactly how it works. And the reason why is because when C allocates a structure, it will actually allocate 8 bytes for this element here. So there will be that many bytes. So if we were to go and take a size of substruct, it would not equal 9. Because there's going to be 7 other bytes here, so it would be equal to 16. And you can verify that just by creating this substructure and then making a call in C and say, hey, I want to get the size of the structure. And we can actually test that over here. So if I have a long value and a character A, and then in here, I'm actually just going to take this and put it in a new file just so we can compile it. Test.c. It's main. Size of substructure. So if we go into our command line, and I'm just going to compile it, so gcc test.c-o test /test 16. So this is just the size of that one structure containing a long, and a character. So it's going to allocate 8 other bytes for that, or not allocate 8 other bytes to store a value for the character, but there's going to be 8 other bytes of spacing. Now, in order to do that and account for that, we would be here forever. I'm not going to do that right now. Oh, what did I just do? That was a mistake. Restore file. That's more like it. So we're just going to enforce that in the structure or in our framework, we're only using stuff that's 4 bytes or under, and then hence we allocate only 4 bytes. We're actually going to restrict it to only characters, integers, and floats. So everything here will just have 4 bytes, and that way we won't have to deal with any of the trouble of having 8-byte values or stuff like that. It's just going to be this specific, or this restricted. So we're back in our struct framework. So that addresses one of the problems. We're just restricting what we can and can't have. So everything worked as expected there. And I suppose we can test, and I'm going to forget. Service unavailable. Why did this happen last time again? I know this happened last time. Oh, it was 127.0.0.1, I believe. There we go. Okay. So we're going to struct framework, basic framework.html, and we'll find our console. Zoom in the console. And I forgot what we had, but it was a 10, 34, and let's just say that. But we see we have the 10, 34, and then a couple of other values here. And what basic framework was doing was when we hit that button, we called runwasm, which computed a sum here. So there was a sum pointer, and it was able to decode it properly, which is good. And I forget whatever sum did, but it works. However, we're still very limited in what we can and can't do. We can nest stuff. We can have a bunch of integers. We can nest as much as we want, but we're still only restricted to integers and characters and floats. There's nothing. We actually haven't even accounted for floats yet. So what we're going to have to do is we're going to have to create a couple more functions to account for more complex objects like pointers, so reference to something, or lists, which are just going to be, we're going to represent them as arrays, which are in turn just pointers, but we're still going to need to allocate a special or create a special function to encode and decode them. So when I was writing this code, I found that there's just a lot of unnecessary, or not unnecessary stuff, but there's going to be a lot of reconfiguration here. So what I want to do is I want to take all of the functions that we have right now and we're going to rewrite them. We're going to leave the decode functions as are, but the encode functions I want to delete all of them. So encode number, encode structure, and start encode struct. So those 3 there. And we're going to start with creating a new function called encode element. So function encode element. And this will take in the type, the actual object with the type, the buffer, a cursor, and just a cursor. So this will be responsible for this is going to be the function that we call to encode anything. And it's going to start just by determining what we need to encode. So we still have our primitives up here, so character, integer, and float. So what we're going to say is, if primitives dot includes type, then we want to encode it as a number. So we're going to rewrite our encode number function. So function encode num, which takes in the number itself, and I should say encode integer. So encode number, it takes in a number, the number of bytes, the buffer to write to, and the offset. So remember, the offset will kind of work as our cursor in the structure, so we don't have to allocate a new buffer every time. We can just say offset the memory by this number of bytes. Now what we're going to say is just for variable I is equal to 0, I is less than n, I plus plus, buffer at I plus offset is equal to number, bitwise and with 0xff, and then number right shift equals by 8. So we're just taking the least significant bit, and we just, we went over this last time, but this is essentially how we did it. We need to encode it in small endian, so the numbers themselves, the bytes are small, or the bits are ordered in big endian, but the bytes are ordered small endian. So this is how it should work here. This was actually decoding. This is what encoding should look like here. All right. So that's encoding an integer. And we want to do that if the type is not float. Because float doesn't work that way. You can't do a bitwise shift on a float, not in C, not in JavaScript, not anywhere I know of. So what we have to do is we have to say, if type does not equal float, then we're going to encode the number, or encode an integer, passing in the object, and if that's undefined, then just 0, number of bytes, which is just typeset type, the buffer, and cursor. Now, if it is a float, we're going to have to do something else. Because again, the buffer is currently a uint8 array. So it's taking things in as an integer and encoding them as encoding the bits as an integer. We need to make sure it encodes it as a float. So what we have to say here is we're going to take a const, we're going to make a float buffer, a float array out of the buffer. So just like we do a new uint8 array of the memory.buffer, we want to make a float array so that we can actually write floats to the memory. So we're going to say const float buffer is equal to new float32 array, passing in memory.buffer, and we could pass cursor, but that wouldn't be correct, but we'll just keep it as cursor for now. And then float buff at 0 is equal to object, and if that's undefined, 0.0. So we're simply just setting one element in this float buffer at the address as the number. So let's just take a look at what we're doing here. So memory.buffer, where can I write? Oh. So we have memory.buffer, which is an array buffer. And in JavaScript, this is the closest you're going to get to manipulating individual bits. Don't call me. I can't. You can't call me daddy. That's inappropriate. So the array buffer is the closest we're going to get to manipulating individual bits. So for WebAssembly, you're going to have a massive array buffer, but it's essentially just a bunch of bytes. You can't access these bytes. You can't, with an array buffer structure, you can't access them. You can't You can't write to them. You can't do anything with them. You can just look at them. Or you can't even look at them. You just have the object. You have a couple of values. You have a size of them, but you don't have an actual, you can't look into the values. What you can do is when you actually specify to JavaScript how to interpret this array buffer, because this is just values. Let's say fe 0x3c c2 blah 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 blah, whatever you want to put there. JavaScript doesn't know how to interpret this, so you need to pass this buffer into an array so that it does know. So for example, if we say a new uint8 array from memory.buffer, it's going to interpret this as an array with where each byte is an element. So fe, whatever that is, 254, or 3c, whatever that value is, it's going to take those values and interpret them as integers. Then when you say, so r is this, so when you say array at 0, if you get the getter of this, that returns 254. If you say array at 1 is equal to 5, then that just sets this value here to 5. So long as this value can fit in, remember this is also an unsigned integer, you can also do an int8 array, which is signed. So you can access set values, and these values will be reflected in the direct buffer. So these will be reflected up here. So when we set that, that'll be set to 0x05. So we're essentially just providing a wrapper around the buffer to determine how to interpret and write values. So we have to do the same thing with uint or float32 arrays. So new float, oops, not flat, float32 array.buffer. And if we say array at 0 is equal to 15.5, that will be reflected in the array buffer in, why does my mouse stop working? Give me 2 seconds. Sorry about that. There we go. So however you encode this into bytes, let's say it's just 0xFFE1C3 Let's just say it was that. What would happen now is it would take these 4 bytes and it would put them in the array buffer. So in our new array buffer, memory.buffer would equal FFU1C3 2B, and then whatever else was there. And you could take now, you could go back to uint8 array and you could find that FF is 255. Or if you took an int8 array, you would find that that's -1. So it's all just about how we actually tell JavaScript how to interpret the array buffer. And that will allow us to do powerful things. I suppose we should be... never mind. I was thinking about distinguishing between signed and unsigned, but it's all good for now. One more consideration here is that we have a cursor, But again, this is looking at the raw memory, or actually we haven't even passed in memory. But the thing is with buffer, I don't think you can pass in just a uint8 array and that can be used here. So what has to happen is we have to pass in the raw memory. So the raw memory element from WebAssembly to get its memory buffer, to get the array buffer. And then we also have to pass another address, because cursor will be a raw address. But the thing is, cursor is going to be an offset into our structure. But with memory.buffer, that doesn't apply. We need to actually get the address where the memory starts. So cursor equals 0, and then we also need a pointer, which has a default value of 0, and then the address where we start the float32 array is pointer plus cursor. And then this will be reflected in the proper memory address. Okay. So that's primitives. We have our encode integer function. Now let's write our encode structure function. So function encode struct. Here we're going to pass in all the same parameters. So type, object, buffer, memory, offset or cursor is equal to 0, and pointer is equal to 0. So this encode structure function is going to assume that buffer has already been allocated. So we have to first allocate our cursor. Well, cursor is already allocated. And then what we do is we're just going to iterate through the elements like we have before. So this code is going to look the exact same. So for const key and type of object.entries structs at type, sorry. So we're just going through each element in the structure format. Share the linear memory access. Do you just mean with the memory buffer? I'll come back to the screen at some point for sure. But when we look at pointers, I'll go into more detail. WASI, I don't think I will be covering that right now. It's not on the plan as of now. But for each element in the structure, we're just going to call the encode element function, encode element. And we're going to pass in the type, or sorry, this will be element type. The value will just be object at name. We're going to pass in the buffer, memory, which is the raw WebAssembly memory, cursor, and pointer. And then we need to say cursor plus equals types at type. Or, you know, this will actually, or we'll keep it at this for now, but it won't work in the future, or in a bit, once we introduce pointers, because that has special syntax. Okay. So we have our encode structure function, and we can now say else here, and then we just call encode struct, passing in the type, the object, the buffer, the memory, cursor, and pointer. So this provides us with the same recursion that we had before. where if you go to encode structure and you have a structure within your structure, it will just call encode element, and encode element will then find this function and call it again. So we're still going to get that level of recursion, which is exactly what we want. All right, so this is all good and all. However, we still don't have our entry function. We want to, right now we have a function called, not numstruct, basic framework. We have a function called start decode struct and start encode structure, which passes in the memory and just a malloc function and then the structure. We don't have the same thing over here, and we don't want to force the user, the coder, to have to create their buffers every time, their arrays every time. We want to do that in a function here. So what we're going to do is we're going to provide several different entry points. Encode struct will not be one of them, because again, we can't just deal with structures as arguments. We have to deal with pointers. Encode integer could be one of them, but you would need an array here. So we're going to have a function called encode pointer, which takes in a type, an object, memory, and malloc. So this is exactly what the previous entry point looked like. And we'll have a check here saying if not object, then return 0. This is just null. And then we're going to say variable pointer is equal to malloc. So we're going to call malloc with types at name. So this pointer is going to be integer pointer, array, character pointer, however we want to do it, but it's going to be a singular element. This won't be an array. This is going to be covering a singular element. This actually has to be types at type. And then we have to get our buffer here. So let buffer, I'll say const, buffer is equal to new uint 8 array, since we're working with bytes, memory.buffer, pointer, and types at type. Oops. So this is just, again, providing that wrapper around the memory that we needed. It's offsetting it by a pointer and just giving us as much space as we need for the current structure. Then we're just going to say encode the element stored with the pointer, stored with the object. However, we're going to tell it to encode this element at a specific address, and that's where the pointer argument comes in. So we say type, object, the buffer is buff, memory will just be the raw memory from WebAssembly, cursor is 0, and pointer is going to be the pointer. And then we return the pointer at the end. So essentially what we're doing is, let's say we were told, hey, I want to store an integer pointer, a is equal to 5. Or sorry, we have to say malloc size of int, and then the dereference of a is equal to 5. The way we're going to do this now is, or how WebAssembly will work with this in this framework here, is it takes our array buffer, and this is equal to memory. We then call wasm malloc with 4, so the size of 4 bytes, and wasm malloc again is going to be from our exports. It's what we define. It's what we just define in C as allocating memory. We're just giving the responsibility to C itself and not to WebAssembly. So wasmmalloc 4. And then we have to get a pointer here. And then what we want to do is we want to create an array around memory starting at the pointer. So if this is our memory, blah, 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 blah. Let's say pointer is equal to 2, or no, let's say it's equal to 4. So if our array buffer is 8 bytes long, we say, hey, let's create our array and we'll start it at 4 and we will have it be 4 bytes long. So the array, the buffer, is equal to new uint8 array. And this will just be the buffer, so memory.buffer. The pointer, so 4, and the size, which is also just 4. And then we can call encode number on this array, and it will allocate whatever numbers, so 5, 0, 0, 0, if our number was 5. So we are simply, with the pointer, we're allocating the memory. So this is where we're actually creating that wrapper. And then this will be an entry point. So when we call nested struct, or when we call start encode struct, this can actually just be renamed to encode pointer. And the arguments are the exact same. So we can actually go ahead and try this. And I'll just call encode here. So we have to recompile here. So emcc, and we have nested struct.c -o nested struct.js. Oh, it's going to do all this stuff and then it should be good to go. I think this is a one-time thing though. So while I'm waiting for that, all we've done as of now is just essentially we've replaced the entry point for start encode struct with a more general method that we can use for pointers in general, not just structures. Because this doesn't really care about what we're encoding. We are just saying, hey, encode the element, and that's going to determine what type and how to encode it here. This needs to keep going. I probably should have done this beforehand because all this loading is not too professional. Come on. Here we go. Okay. So if you ever new stuff, I'm going to reload, and then I'm going to call encode like that. Integer divide by 0 runtime error. Where? Basic framework.html. 69. Can't see what's compute sum. Or wait, hold on. This might be why. All right, encode pointer. I think we need to do some stuff here, or some logging. Console.log allocated types at for the type. Allocating 16 at this for struct. That sounds about right. Something going on. Oh, because there's something with not providing malloc, I think. Yes. Encode pointer takes in malloc, and we need to pass that along to encode element. So we need to pass in malloc before the cursor. And encoding the struct does not need, or actually encoding the struct does need malloc. However, it shouldn't right now. But we essentially just need to, oh, yes. All right, this is why. It was passing in cursor for a function definition. So we need to fix that. So malloc is here, and then encode structure takes in memory, then malloc, cursor pointer. That gets routed there. This gets routed here. This gets routed here, and it's not in there. Nope, it's still not. Okay, so that wasn't the issue. Okay. Console.log, encoding. Offset by cursor. All right, encoding. Oh, I see. I think I know the problem. Yes, that's why. In encode structure, we were incorrectly incrementing the cursor. This needs to be typeset element type. So the length or the size of the current element, not the structure. My mistake. Now this should work. There we go. 391910. So this is the expected result, and this is what we got from the integer division. So it's working. Encode pointer is working well. So what if we had something where, let's say let's say in our structure we wanted to actually just store a pointer. So we have this element pointer, which just stores something like that. Can we do that? And the answer is yes, we can. And the way we would do that is when we register a struct, we would just pass in the value, because remember, we are interpreting pointers here as single elements. So this would be a pointer, and we'll just say is 15, like so. And then in nested struct.c, we have to reflect this integer pointer, and we'll have a function just to get that value. Integer get pointer. So return the dereference of s.pointer. So we're getting the pointer address and we're dereferencing it here. So let's recompile. Error. Uh-oh. Expected. What do you mean expected? Do I have to do this? I guess it doesn't like that syntax. Oh, because I was using the type, that's why. Okay, make sure you use the element name. I really don't like that IntelliSense or the coloring doesn't work because it doesn't recognize this tag here, but it's all good. There we go. Okay, so we now have to determine, all right, well, hey, when we get, so if we just try to do this right now, let's see what would happen if we just tried to do this right now. It wouldn't be very fun, or actually we need to write the function to actually get it. Integer pointer is exports.get int pointer. So we're just passing in the structure. Again, the pointer represents the structure. So reload this. Encode. Can't convert undefined to object. Yes, that's why. Because it's trying to encode this integer pointer, but it doesn't find the integer, or it doesn't find this type. So what needs to happen is in an encode element, we need to determine, hey, is the current element a pointer? Because primitives has these three elements here. There's nothing that says integer pointer is a primitive. So what we have to do is we have to have an if statement. So I'll put that up top. So if type dot ends with a star. So if it ends with a star, then we're doing a pointer. So we're going to recall our encode pointer function. So what we're going to do in encode element is when we find the pointer, we're going to first get the pointer. So const pointer is equal to encode pointer type.substring. So we want to get everything but the star so we can identify the type. So 0 type.length -1 object memory and malloc. So we now have the address. And with the address, this is what we're going to set in the actual, in the structure. So encode num pointer for buffer cursor. So if we try to do this now, calling encode num is not defined. And you can see in the logging here, so it's encoding 15 integer pointer at this and offset by some value. However, it sees that it's a pointer, so it then allocates the elements or allocates memory for it, encodes it, and then it's saying encode num is not defined, or it's encode integer. That's why, because the pointer isn't an integer. Oops. Get int is not a function. Uh-oh. What did I name it? Get pointer. That's God. There we go. Oh, no, that's not right. So something did not work here. So it's encoding sub pointers 15. 10, 34, pointers 15, and then the object. Allocated not, yes, that's right. What happened was it didn't know how much space to allocate because, again, it doesn't types that integer pointer, it does not exist. So what we need to do is when we're computing the size, we also have to have a special case here saying if type dot ends with a star, then we're just going to add 4. So size plus equals 4. And else we actually find the elements there. So now, again, the only change is just setting the size. Then we call encode. There we go. So this is our sum from before, and integer pointer is 15. So it successfully found the encoded value here and at this specific pointer. Now, what if we wanted to do a multiple, like a double pointer, so a pointer to a pointer? Well, you could do that. We would have to modify this framework a little bit. And it'd be rather simple. Because encode element, I actually don't even think we have to. Let's try modifying this structure to take in an integer double pointer. So then it dereferences both. Like so. All right. So if we try to do this now, we would need to say, all right, basic framework, our integer has to be a double pointer now, but it's still going to take a value. So if we reload here, call encode, integer pointer here is now this, which is, let's see what it did. So it said encoding 15 integer at this by, okay, so what happened was, again, it didn't find the size, and this is the one modification we do have to make. Typeset type. Let's just create a get size function, or get element size. So function get element size type. So if type dot ends with a star, then we just say return 4. Otherwise, we return typeset type because it's in the array. And then in compute struct size, we're just going to say size plus equals get element size with the type. And then in an allocate pointer, we're going to say malloc passing in get size type. We can actually just say const n is equal to get size, just so we don't have to call the function several times. Like that. Okay. So we reload, and let's look at the log here. Get size not defined. Get size is not defined. It's get element size. There we go. Still a couple of problems here. So we have our structure, which is allocated all fine, that computed properly. So we have encoding 15 integer double pointer at 524440 offset by 16. Oh, I believe what the problem is. So encoding 15 at that, offset by 16, allocated 4. Encoding 15 integer pointer. So that's fine. These addresses are getting propagated correctly. Let's just say console.log setting pointer at cursor, just to see what actually is going on with the memory addresses. So setting, okay. So encoding this double pointer allocated, encoding single pointer allocated, encoding that offset by 0. So setting, oh, is this might be, okay. Setting 52444. No, this is right because it's setting the pointer at 0. And then it's setting 5244464, which is the address of the first pointer. Setting that at 16. It might be that, you know, let me just do this. So object.pointer at 0 at 0. Let me just get the actual element instead of trying to do a dereference, because that might be what the problem is. There we go. Integer pointer is 15. So it was a C problem. So we're now able to propagate multiple pointers, which is wonderful. Sorry, give me 2 seconds to go fill up my water. All right, I'm back. So, again, we now have the capability to do any number of pointers. All right, now what we want to do is let's look at arrays. So again, pointers only cover one element. We want to do multiple elements. So we will say arrays must be indicated with this syntax here. So we'll say int array is going to be integer with brackets, but this is just interpreted as an integer pointer, like so, in the structure. Because if we were to have that, we would need to specify a size, or I suppose not. It doesn't look like it. I suppose you actually don't need to. That's true. Cool. So we want to be able to specify this as our type. So in struct framework, let's start just with get size, just so we can get that out of the way. So get element size, type.ends with a pointer, or type.ends with a square brackets. If that is, then we're just allocating a pointer. We're going to create a new function called encode array. So function encode array. We pass in the type of the array, the object, so the array, memory, and malloc. So you can see how all of these two entry points, the encode pointer and encode array, these will actually be, these have the simplest parameter set. Because we're just taking raw memory, and since we're getting a custom address, we don't care about what previous buffer we may have had. we're simply just creating new memory somewhere. Or not creating new memory, but allocating new memory somewhere. And we'll do the same thing. So if not object, then return 0, which is just null. And then we're going to get our element size, or the size of the array. So const n is equal to array.length times get element size type. So we're just going to worry about stuff like integer arrays and pointer arrays or stuff like that right now, but we will look at strings right after. So the way we're going to do arrays is we're not going to worry about any silly little dynamic arrays that or dynamic lists that we looked at last time. We're just going to assume all data is constant. We don't really care about we don't care about resizing the data that we pass into C, because what WebAssembly will be used mainly for is taking in data and processing it, not necessarily outputting a lot of data or adding to lists. But for now, we're going to say array.length plus 1, so we can have a terminator element. Okay. So this element size, or we're just going to allocate an end element so that when we're in C and we find, let's say we had an integer array, we have, let's say this is our 4 bytes. Let's say it was 5, 3, -2, 1, and 0. So 0 would be the terminator element. And I suppose this might be a little confusing or improper if we do in fact have a 0 at the beginning, something like that. So what could also work is you pass in an extra element saying size, which is an int, and that takes in array.length. And we're going to compute this on JavaScript. So we'll say, for example, so integer array, and then we also have array length, which we'll just say is an integer. So when we encode this integer array, let's say this is going to be 5, 2, 0, 15, -2, like that. And then we also pass in an array length, which is just going to be 5. So the integer array and then array length, two separate things. And this will be hard-coded on JavaScript side. And then in our C code, when we do an analysis on this array, we don't look for a terminator element. We just look for this number of elements. So we can customize how we interpret that here. So we're allocating that number of elements, just in case we do want to have a terminator. Just a little trick. So we're going to allocate, we're going to do malloc, just like we did with pointers. So the first part of this will be almost exactly like the encode pointer. So const pointer is equal to malloc n. Then we're going to create our buffer. So const buff is equal to new uint8 array memory.buffer pointer and n. Then let cursor is equal to 0, and then for variable I is equal to 0, I is less than array.length I++. Then we're just going to encode each element separately. So we're going to call that encode element function and allow it to deal with it however it pleases. So encode element name array at I, type array at I, buffer, memory, malloc, cursor is the offset and the pointer, so PTR. And then we need to advance the cursor. So cursor plus equals. We're actually also going to get an n singular. is equal to get element size type, and then we can use this instead of calling get element size every iteration. Okay, and then afterwards for the terminator element. So encode number 0, n individual, so the number of bytes, buffer, and cursor. So again, this is going to be sorry, what am I thinking? This will be the terminator element, and this will be within the local memory that we have allocated. So let's try doing something. So we have basic framework, which does this. And let's create two different functions, one that computes the sum of elements. So we have integer array, and then we also have integer size, or our size. And let's say we have mscript and keep alive. So we'll say integer comp sum terminator, which just looks for a terminator element. So integer pointer, or sorry, s pointer object. So all this does is so we have an integer sum is equal to 0, integer I is also equal to 0. And we're going to say while array at I, so an unknown length of something. So while the array at I, sum plus equals the array at I plus plus. So we're just incrementing the sum every time we get into an element that's not 0, and then we return the sum. But let's try doing it a different way. Let's do mscript and keep alive with an integer compute sum array, or compute sum size. So we've taken an s pointer object here, and this will do the same, except this time we're not going to be looking for a terminator element. We're just going to be iterating through the values. So integer sum is equal to 0. For integer I is equal to 0, I is less than object dot array size I plus plus, sum plus equals array at, or object dot array at I. This needs to be object dot array, and then we return the sum. So you choose which one you want to do. This will be needed if we do in fact not have, or we do know that there will be 0 elements, or elements that have the value 0, but that may not always be the case. So we shall recompile. Someone didn't like it. Flexible. Oh, yes. So we cannot, in fact, have an integer array. It needs to be a pointer, unless it's at the end. But I'm going to say integer array pointer, just for that. Oops. And just make sure you have the correct name. So we cannot use the array syntax here because it doesn't know how long it is. So it may, so it doesn't know what the size of this structure is. But it can be flexible. Okay, so we have that, and let's go and do a couple of things. So console.log terminator sum is exports dot, and we called it compute sum terminator with the pointer, and then console.log size sum is exports dot compute sum size with the pointer. And let's just compare our results here. So I'll just recompile just in case, do a quick reload, hit the encode, something didn't write, something didn't happen well. Allocated 28, 28 looks correct because we have, what's in our structures? We have 1, 2, 3, 4, 5, 6, 7. So 7 times 4 is 28, so we have 28 bytes, which is correct. Where was the NAN? Offset by NAN. Struct framework 81, line 81. What didn't it like? Wait, no, I don't want that. Encode structure. Can't convert undefined object. So the offset is by cursor. So we're not passing in cursor to, because we don't even allow it to be an array, right? Encode element, right, that's my mistake. So in encode element, we, just like we have the if type dot ends with pointer, we also need to allow it to end with an array. So the array brackets. So we took care of that in the get size, but not here. So we'll say else if type dot ends with square brackets, and in this case, then we're going to say it's going to be the exact same as pointer, just with a couple of different arguments. So const pointer is equal to encode array this time, and in encode array, we better return pointer. So encode the array, passing in type.substring 0 and then type.length -2, because this time we need to chop off the 2 square brackets. Object, memory, malloc, that's stats. And then encode integer, pointer for buffer, cursor. Just like so. So let's hit a reload, encode, something doesn't like it, array is not defined, thank you, I missed something. Yes, encode array takes in an object, not an array, or takes in an object, something named an object. I really need JavaScript IntelliSense to work better. Nope, still doesn't like it. 69, it's pretty cool. Object dot length +1. There we go. Nope, encode num is not defined yet. Encode integer. Or encode elements. No, encode integer. Because we just needed a 0. Right? Yeah. Because this will just compute the size and it will just give us a bunch of 0 elements instead of recursing into encode element any further. Save us some processing. Encode. Terminator sum is 0. Alright, so it's compiling, which is good. But it's still not like in the offset. So encode. Why is it encoding 5 integer offset by NAN? Ah, wait. Offset by encode elements. Why is it printing this? 0, 4, 8. That's the correct. So 5, 2, 0, 15 minus 2. What's our array again? 5, 2, 0, 15 minus 2. What's this other 5 for? Oh, the length. That's why. Huh. What's up with that? So that's an encode structure now. Alright, so it doesn't know what array length is. Um, 5, 2, 4, 4, 4. Okay, so it lost the offset. It lost the offset at the array. Well, this is fun. So after it went through the array, cursor pointer, type object buffer. Wait, this is array. I need structure. Type object array buffer. Memory malloc cursor pointer. What? Oh, because yes, that's right. It didn't know what type set element type was, so we have to say get element size element type. And there we go. So again, just update your references to the dictionary so that it actually does things properly. There we go. So terminator sum is 7, size sum is 20. This looks right because the terminator sum, so if we look at our array, the terminator sum will only read the 5 plus a 2, and then it sees a 0 and says no more. So it doesn't like that at all. Or it just says 5 plus 2 is 7, which is what we saw here. And then it says size sum is 20, so it says, because it's looking at all 5. So 5 plus 2 plus 0 plus 15 plus minus 2 is 20. So that's the array. Let's do one last quick thing with strings. So in encode array, we're going to say in encode element, we're seeing if type is equal to char. So we're going to make sure that people do in fact say strings are character pointers. That's non-negotiable. So name so if type is equal to character, then we're going to say we're just going to take the buffer at I is equal to object at I. So we're just going to send the characters over. And then say cursor plus plus. I actually don't even know if we need a cursor at this point. And then after the loop, you know, we can just say this. If type is equal to char, then we're just going to do a simple loop. So for variable I is equal to 0, I is less than object.length, I plus plus, then buffer at I is equal to object at I, and then afterwards we say buffer at object.length is equal to 0. However, we need to do a couple of things here. An individual can only, if its get element size needs to be type is equal to char. If that's true, then 1. Otherwise, get the element size. Because if it's a character, then, you know what? Let's just make the, you know what, no, we will make the element size of a character just be 1. Even though it's not aligned that way. We're just going to say don't use a character in your structure, because this will get screwed up otherwise. But I'm going to find a workaround for that. So if it's a character, then we're encoding a string. So we're simply going to copy the elements over, copy the characters over one by one. And then let's create in here, let's have our character pointer name in the structure. Character pointer name. So mscriptin keep alive void print name, passing an s pointer object. And then I want to be able to print this, but I don't, I want to just see it in JavaScript. So let's use an exported function. So that'll be extern void print name, or print name to console. And this will pass in a character pointer string. So print name will just say print name to console, passing an s dot, or object dot name, like so. And then since this is an exported function, we have to define this. So if I go and compile this here, it's going to give us a couple of errors. But if I look at wasm2wat, and sorry, let me just do this. Nested struct dot wasm reveal in file explorer. Okay, so this is the wasm2want, and you see that it's trying to import a function called named print name to console. So we need to define that function in our JavaScript here. So when we say the environment, let's create a function here. Function print name, which takes in an integer pointer. So this just takes in a pointer. Print name to console. It's just print name. And we can go ahead and say console. We have to get the string at the pointer. And we've done this before with memory, where we did memory.js. No, not that. malloc.js. Nope. malloc.html. Yes, decode string. Here we go. So we need to take this decode string pointer, paste it into basic framework, and then print name will just say const str is equal to decode string, passing in the pointer, and then we're going to say console.log found name string at pointer. So it's going to print out the string and then the value of the pointer. So if we have now this name here, let's pass in our value, which is just WebAssembly, like so. Have to do some recompiling just to make sure. reload, encode. We actually need to call this function exports dot exports dot and the function was called print name, just like that. Takes in no argument, or actually takes in the pointer. Reload, encode. All right, so getting name, found name, empty string at that. All right, so encoding WebAssembly character at this, blah, 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 blah. Allocated 1 at, oh, yes, that's why. Wait, sorry, encoding this character, blah, 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 blah. Character pointer at 52444. So 32, that looks right. And then allocated 1 at that for character. Oh, because it's not a character pointer, it needs to be a character array. That's why. That's why. Okay. Not a character pointer, a character array. Then we reload. Encode. Found name, empty string. It's still not liking it. Encoding this character at 52444. Offset by 28. So it's still saying 32 is the size, meaning there are 8 integers, which is so 1, 2, 3, 4 for the substructure, 5, 6, 7, 8. Good. Then instruct framework. I'm just going to do some logging here. Setting string WebAssembly 11. And individual n. Just let's see how much memory it actually sets. 1 and 12, so that's correct. So it's still saying buffer. That is fine. Oops, sorry. So it's doing that as good. It might just be that it's not liking how it's encoded, but or it might not be like in the output, but let's go to our basic framework and just print out console.log new uint8 array memory.buffer the pointer and then 12 characters. Nope. All right, so it's all zeros. Okay, I'm not sure what's up there, but either way, I will worry about that later. So that's arrays and pointers, and we're pretty much wrapping up these structures in WebAssembly. We're going to do a couple cool projects with this structure decoding, and we will see what that looks like in a bit. But anyways, I hope you guys enjoyed. I will see you guys next time. Have a good one.